Welcome to another exciting educational video brought to you by Upvision Concepts Academy. Today we'll be looking at linear momentum, and in this topic we'll be treating impulse and momentum, the Newton's law of motion. You have the first law of motion, the idea of inertia, Newton's second law of motion, the third law of motion, and every kind of application you can think of. So stick tight to the end of this video to get the nitty-gritty of what we're talking about in linear momentum. If you're not subscribed to our channel, please subscribe to our channel to get more videos. So we'll dive in. So we have impulse and momentum. Impulse and momentum. First of all, the momentum of a body is defined as the product of the mass and the velocity. The momentum of a body is defined as the product of the mass of that body measured in kg and the velocity, okay, in meter per second. So if I have rho as momentum, the formula is m times v, where m is the mass and the v is the velocity. Okay, so a momentum is a vector. It's a vector. So it has magnitude and as well as direction. So the direction of momentia, like velocities, are therefore applied by parallelogram's law. Understand? So, but impulse, on the other hand, is the product of force and the time. Force and the time. So impulse is F and T. Impulse is F and T. So if I have momentum as the rho mv and impulse I as ft, we can see that these two quantities can be related to each other. So I'm going to quickly apply these two concepts in simple calculations. So note, very, very important. This is momentum and this is impulse. So these two concepts are very, very important when we are considering this topic, linear momentum. So I have this simple question on the board. It says a stationary ball is hit by an average force, 50 Newton, for a time of 0.03 seconds. What is the impulse experienced by the body? So this is simple, knowing that the formula for impulse I is equals to Ft. Okay, so in this question, we're given that F is equals to 50 Newton and time is given as 0.03 seconds. So to get the impulse, it's a product of the two of them, 50 times 0.03 seconds. So the answer is 1.5. So the unit of impulse is the combination of these two. It's a derived unit. So you have Newton, then per seconds, or Newton slash N slash S. Newton per seconds. Newton per seconds. Okay? Newton seconds. That is the unit of impulse. So we'll dive into another example that would describe momentum. So this second example is saying a body of mass 3 kg moves with a velocity of 10 meters per second. Calculate the momentum of the body. So we are given that momentum, okay, I represented it with rho, is equals to m times v, where m is the mass and v is the velocity. So from the question we plug in, momentum is equals to 3 kg is the mass and velocity is 10. So by the time you multiply it, you have 30 kg ms seconds. That is 30 kg meter per second. That is the unit of momentum. So these two examples we just saw is a practical application of momentum and impulse. So take note of these two ways of applying this. Okay, so there are three laws of motion, that is Newton's laws of motion. The first one is the law of inertia, the idea of inertia. So you have Newton's first law. This is how it is. Secondly, you have Newton's second law. And thirdly, you have Newton's third law. Okay, this is how we have them. So, but the first law, Newton's first law, actually deals with inertia. What is inertia? Let me put it here so you see inertia. Okay, so the first law states that every object continues in a state of rest or uniform motion in a straight line unless acted upon by external force. So every body, so this is the first law now. Every body, if I put, okay, let me put a vehicle here now. A vehicle stationary like this. So the vehicle that's not moving is in a state of rest. It remains like that. If it starts moving, it will continue to move perpetually. That is what Newton's first law is saying. But the only thing that can stop it is when friction is applied and when brake is applied to it to stop it. So Newton's first law tends to describe that a body will continue the way it is, either resting or in motion. If the body is resting, it will remain perpetually at rest. If it is moving, it will remain perpetually moving. That is what Newton's first law is. And you see that you can describe a situation where you are in a vehicle that is moving, for instance, and a brake is suddenly applied to it. When the brake is suddenly applied, the people inside of the vehicle will tend to jerk forward as if the motion is continuing, as if they are supposed to be continuing the motion. Meanwhile, something else is stopping them. So that's jerking forward because of abrupt stopping of the vehicle is described by the first law, because your body wants to continue moving. Meanwhile, something stopped it. You understand? So on the flip side, the car is stationary and it just all of a sudden moves with a speed. Just move with initial speed. You see that the people in the vehicle will jerk backwards, as if to say, let them continue to remain where they were. But the motion, the movement, push the body forward. So Newton's first law is the law that describes inertia. Inertia has to do with a body that is, trying to remain at rest. You understand? The nature of the body at rest. That is what inertia is all about. Okay? So in summary, Newton's first law states that every object continues in a state of rest or of uniform motion in a straight line unless acted upon by an external force. So this is key. This is key. If this does not happen, that body will continue to be in a state either of rest or perpetual motion. So we'll dive into what the second law is saying. Okay, so now Newton's second law states that states that the rate of change of momentum is directly proportional to the force impressed in that direction. So change in momentum, this is the expression of Newton's second law. Change in momentum is proportional to the force applied in direction of the momentum. Okay, now we know that momentum is defined as mass times velocity. But you know, the Newton's second law is talking about rate of change. Yes, rate of change. Rate of change. So rate of change has to do with time. So the momentum per time is equals to, or is directly proportional to the force, F. That's what Newton's second law is saying. That the rate of change of momentum is proportional to the force impressed in the direction of that force. So this is the mathematical expression of momentum, understand? And of second law. So you have the momentum as m times velocity over time, which is the rate of change of momentum proportional to the force. Now, if the constant of proportionality is removed, I can flip it. So F is equals to mv over t. But recall in your analysis of linear motion, we know that A, acceleration is the rate of change of velocity per time. So this component is acceleration component. Okay, so I have F is equals to m times A. So where F is the force, m is the mass, and A is the acceleration. So the Newton's second law, in effect, describes the formula F is equals to ma. That is where we get the concept of force is equals to mass acceleration. Okay, of course, there's a constant in this because I remove this proportionality sign, and normally when you do that and increase the equal sign, you will put a constant. So this constant is just there to show that everything is equal, that everything is, the condition is right for this to happen. Okay, but most times it's normally 1. It's normally 1, so that you now have it as F is equals to ma. So of course we know that the unit of force is Newton, unit of m is kilogram, and acceleration is meter per second square. Okay, so we see also that we recall before that I told us that we should note these two formulas. Momentum is equals to mv, and the impulse is equals to ft. So here, this second law can relate these two concepts. How? Okay, let me show us how. Okay, so I'm going ahead to show us how impulse and momentum are related. Okay, so from the concept of F is equals to ma, right? We know that F is equals to m times A, where A is the change in velocity per unit time, recall. So if I express this further, m times v is mv, where v is the final velocity, minus m times u is mu, where u is the initial velocity, all over time. If this one multiplies F, that is time multiplies force, I have Ft is equals to mv minus mu. All right, so this is just change in velocity. All right, so and this is change in velocity. That's velocity initial, final velocity v and initial velocity u, and m is constant. I can just put it simply. Ft is equals to m open bracket v minus u. It can be in these two forms. So this is what I have. So this part of this equation is the impulse, and this part is the momentum. So momentum and impulse and momentum are related using the second law. So if you see that in your objective in the WAEC, you can also tick this as an option. The second law relates impulse and the momentum. Okay, so we see that using the second law gives a measure of force as the product of mass and acceleration. Hence, acceleration is given as from here, you can say acceleration is A is equals to F over m. Just simply making it into the formula, you get that relationship. The second law of motion also gives us operational definition of force as the rate of change of momentum per time. See another concept. So this one is the first one, this one is the second concept. that the rate of change of uh, uh, of momentum per time. Okay, let me use this one. Let me use this side. What I'm trying to say now, this describes the rate of change of momentum per time. So momentum is changing from one state. This is the initial state, and this is the final state. Why am I saying this is initial? Because I have initial velocity here, and this is final with final velocity here. So it's changing from this state to this state, and the rate of changing is equal to what? The force. So this second concept is also important. You can see that in your objective. Please take note. So we'll go into simple applications of this concept with questions. Okay, so a simple question on the board. It says an unbalanced force of 20 Newton acts on 4 kg mass. What acceleration does it give it? Okay, so I have two parameters here. Force is 20 Newton and mass is 4 kg. And I'm asked to get acceleration. So what's relating these three different parameters is this formula. F is equals to ma. Remember, this formula stems from Newton's second law. So what do I have and what is missing? I have force. Force is 20 Newton. I have in the question I have mass. Mass is 4 kilogram, and I don't have acceleration, which I must find. So I say plugging it into this formula. F is 20, m is 4, a is unknown. Make it equal to formula. I have 20 over 4 is equals to a. Simply a is 5. 5 what? 5 meter per second square. So this is the acceleration that we are looking for. Okay, so I have another question on the board. It says a 900-gram stone is pushed along a tarmac by a horizontal force, 20 Newton. A frictional force of 8 Newton opposes the motion. What is the acceleration given to the stone? Okay, let me represent the stone like this. This is the stone, and it's on a horizontal tarmac. Sometimes it's good for you to represent the question in a diagram form so that you can appreciate, you can imagine what is going on. So this is the stone. The stone's mass is 900 grams, okay, and it is being pushed on the tarmac. So this is my tarmac. This surface is tarmac, okay, by a horizontal force. So this is another force here, horizontal. This force is pushing it this way. So a frictional force of 8 Newton opposes the motion. So where will this frictional force be acting? To be acting opposite this one. It's going this way. So it gives you a sense of this one opposing this one. So the force that is meant to move this is not this. It is this minus this. The force that is meant to move this stone is not 20 Newton. The force that's meant to move this stone is the difference between this force on it, pushing it to the forward, and the force opposing it. So this force now is the frictional force. Frictional force. And what does it do? It opposes. It opposes. So it goes the other direction. So it has a way of reducing this one, the effective force that will move this, reducing this one by its value. Okay, so in effect, we are now told to find the acceleration of this stone. Okay, now we know that force is equal to ma. This force is not this one. This force here is the difference between this and this, because this force that will move this stone in a given acceleration is the net force. We call it net force, and net is just like a resultant. So this force F will now be the difference between 20 and 8. That's why I have it like this. And the mass is 900 gram. Of course, we are converting it to kilogram because we are going to work with SI units standard. SI unit standard. Already the force is in Newton, so this should be in kilogram. So I will say 900 divided by 1000. Why? Because I am converting this gram to kilogram. Then times A. A is unknown. A is unknown. Okay, so the difference between this and this, the net force, this is 20 going forward, 28 going backwards. Backward force is the frictional force. So difference between 20 and 8 is 12. So 12 is not the force that will move this thing forward. Yes, that's the force. It's not stated here, but you have to derive it. Okay, so 12 is equals to, this is 0.9, that is divided by this, and times A. So A will now be 12 over 0.9. By the time we compute, we'll be getting 13.33 meter per second square. So this is the acceleration of this body. Okay, so I have on the board question 3. It says a ball of mass 0.3 kg moving at a velocity of 20 meters per second is suddenly hit by a force of 5 Newton for a time of 0.3 seconds. Find its new velocity of motion. Okay, now in the question we are given mass of a body. This is mass of a body. We are given velocity of that same body, and a force F is, hits that body for this time. Find its new velocity. Now, what this thing is trying to paint is Newton's second law that states that relates force with change in momentum. That is force with the rate of change in momentum. What is that law? Remember, I said force is equals to mv minus mu all over t. This is what we call the rate of change of momentum. That is this is u. U is initial, momentum initial, and momentum final. The difference of the two of them per time is known as rate of change of momentum. This particular component is the rate of change of momentum. Yes. So why? Because I have two components of momentum, initial and final. The difference and the rate of that difference is momentum rate equals to force. So this is what we are looking at, and this is what we're going to be using for this particular question. So if I bring out my parameters, I actually have mass m. Okay, let me just simplify this. F is equals to m open bracket. M is common, right? V minus u all over t. Okay, so I'm looking for a new velocity, final velocity v. Every other thing is given here. I can bring it out. F is given as what? As 5 Newton. M is given as 0.3 kg. What else? Initial velocity u is given as 20 meter per second. What else? And time is given as 0.03 seconds. Every other thing is given. I have 1, 2, 3, 4 parameters. I have 1, 2, 3, and 4. So I'm looking for V final. So let me just make V such a formula. Okay, so this can come up here. That's force times time. So I have it as Ft. Remember, Ft is what? Impulse. It's impulse. Ft is equals to m v minus u. Of course, Ft over m is equals to v minus u. So I can leave this one here. So Ft over m plus, when u comes to this side, it becomes plus u is equals to v. So v is standing alone, so I can find it. When I plug in everything I have here, I'll find it. So F is 5 Newton, T is 0.03 all over, M is 0.3, of course, then plus u. U is what? 20. So I will do all these maths like this. I will get this times this, divided by this. I'll get this like this and add to this. By the time I do that, it's simple maths now. So V that I'm looking for, this V, will now become 20.5 meter per second. So this is the final velocity that we are looking for. So questions like this just is for you to relate what you are given to the particular formula you will be using. Okay, the particular concept. That is why you should, in physics, understand the concept. That's why we started by defining momentum, defining inertia, defining impulse, then talking about the second law of motion, this second law of motion that talks about the rate of change of momentum, direct proportional to the force. You know, many things can be deduced from that particular statement, and in that particular statement is what is making us to solve these questions, this particular question, and getting the answer. So we'll quickly move on to the next one. Okay, so we have the question on the board, number 6. It says, a body of mass 0.1 kg dropped from a height of 8 meters onto a hard floor, bounces back to a height of 2 meters. Calculate the change of momentum. First question. If the body is in contact with the floor for 0.1 seconds, what is the force exerted on the body, given that gravity is 10 meters per second square? Okay, now the first thing we should do is to calculate the change of momentum, or change in momentum. What's the formula for change in momentum? Recall that we said change in momentum is equals to mv minus mu, where m is the mass, v is the final velocity, and u is the initial velocity. Now we can illustrate this this question with a diagram. Let's say this is the surface, the ball of mass. This is the mass, this is the ball. The mass is 0.1 kg, 0.1 kg. From this height, it drops to this particular point. And distance between where it was before to where it dropped to the ground is 8 meters. And from here, this is one instance, this one instance. At another instance, they are meshed together. On that instance, it bounces off to a point 2 meters up. So these two are actually meshed together. I don't want to draw the diagrams to be close to me to be in one, but just imagine it as one, but I'm separating them to show you there are two instances. First instance was where the ball was up here, it goes to the ground and bounces off, and when it was on the ground, yeah, it bounces off again to this particular height. Now, the question is very simple. We're told to calculate change in momentum. So I have mass already. I have mass already, but I don't have final velocity and initial velocity. That's where this diagram comes in now. And you know, in our relation, trying to deal with linear momentum, always also remember your linear motion equations. Recall this equation. V squared is equals to u squared minus 2as. Remember this equation. Remember this equation. Okay. Okay. So this equation will be useful here. But you know, this A, acceleration, will now change to G. Of course, when you change to G, I'll change one to plus. So I need to find one component or two components. I need to find V and U. If I can find V and U, I will get this question, because I don't have V and U, but I have M already. So this first part of this question, I can get it. So I have dissected these two diagrams, though they are one instance, that's one situation. The ball from a point goes and hits the ground and returns again. Understand? So I have separated the two instances. So for this first instance, the ball at this height, the ball's initial velocity is 0. So when it starts going down, there's a final velocity. So for this first instance, I can get this, I can write this like this. V squared is equals to U squared plus 2A, G. Because I'm changing on to G, I'm changing on to plus. Why? Because gravity is acting downwards. Okay, so that's why this one is plus. Okay, so, okay, that's G. Now, at this height, V is equals to 0. Sorry, U is equals to 0. So at this height, U is equals to 0. So V is what I'm looking for, and U is already equal to 0, plus 2 times, my times is a dot here, 10 times s is what? S is the distance. So distance for this particular instance is 8. Is 8. Okay, so we are in business. So v square is equals to, this is already 0. This is 2 times 10 is 20. 20 times 8 is 160. So I can get v as square root of 160. So v is equals to, by the time I compute, I have 12.65 meter per second. So I've gotten v. I've gotten v. So I want to go and get u now. U is here. U is here. Now, u is the initial velocity from this point. There's a velocity at this point because that velocity is what will propel this thing up. But when it gets to this point, there will be a momentary stagnation. It will just cease there. As it's ceasing there, at that point, v is 0. At this point, v is 0. Just imagine motion. The ball is from this ground is bouncing off. As it's bouncing off, something is propelling it up. There's an initial velocity which is u. So if I say apply this formula, v square is equals to u square plus 2gs. U is having something, v is equals to 0 because when it gets to the final point here, no velocity. So v is equals to 0. So at this instance, v is equals to 0. At this instant, v is maximum. Okay, so let me continue. So I have u is what I'm looking for, plus 2.10.s is now 2. Why? Because I have this distance as a 2. So I'll quickly calculate. By the time I do the maths, of course, when this one goes this way, I have 0 is equals to u square plus 40. Okay, so at this point now, I'll be having the square root of 40. The square root of 40. Okay, so u square is equals to 40. Okay, now, sorry about this. This is supposed to be minus. I'll tell you why it's minus. Because it's acting against gravity. So that when this one comes here, it becomes plus. Please note, because it's coming down, that's why there's a plus here. You understand? But when it's going up, it's a minus. So that's why I have this. So the square root of 40 will give me u. So by the time I compute that, I'm getting 6.32 meter per second. So I have v, I have u, and I have m. So I can put it here now. I'm coming back to this place. This is the question. This is my question. So change of momentum. So what's my m? Okay, let me just factor it out. M is m into v minus u. M is given as 0.1. V is given as 12.65 minus u is given as 6.32. Okay. So by the time I do this maths, I will get my change in momentum. Change in momentum, very easy. Change in momentum, very easy. Now note again, the dealing of signs is very, very important. Okay, so this change in momentum is actually the definition of change in momentum, but because of what is happening here, the first momentum is normal. Second momentum will now have this minus mu. Okay, let me go. I'm just trying to do economy of space for this board. Okay, so what I wrote before is formula for momentum, but because of this situation that we have now, this is the first momentum, which is the final momentum, minus. Then second momentum is actually acting against it. You're now moving in the same direction. If after the impact they were moving in the same direction, then this one will be positive here. But because it's moving opposite direction, that's why it's negative. So this thing will now become v plus mu. So I have m here outside, then v plus u. So what's my m? M from the question is 0.1, and v, I've gotten it here as 12.65, and u, I've gotten it as 6.32. So when I compute the maths, final answer I'm going to be getting here for change of momentum is 1.9 Newton, 1.9. Okay, what's the unit of momentum? Okay, I can do a derived unit. This is kg, mass is kg, and velocity is what? ms1. ms minus 1, sorry. Okay, so that's the answer for the first question. Okay, so the second question says the force exerted. So I've got my change in momentum. I can take this off because it's what I'm using getting that, so I can take it off. I can watch the video again to see what happened there. So for force, remember that force from second law is defined as change in momentum over time. This is simple enough. I've got my change in momentum already. Force is equals to, change in momentum is 1.9, then the time is 0.1 second, so 0.1. So just simply put, this is 19. 19 what? 19 Newton. 19 Newton. Okay. All right, we'll do a final one. Okay, so I have this final question for this particular episode. A body of mass 2 kg falls freely from rest through a height of 50 meters and comes to rest having penetrated 5.0 cm of sand. Okay. Calculate the velocity with which the body hits the sand, the time taken in falling, and thirdly, the average force exerted by the sand bringing the body to rest. Okay, so now, again, like I said, I try to visualize what is going on. So let me just put it at this small space here, this side here. This is the body. The body is 2 kg. This is the body. So it falls from rest like this. So when you say from rest, that means u, initial velocity u is 0. So let me use broken lines to indicate the space between dirt and ground. So it falls from rest, goes like this, and hits the ground. This is the ground here. Hits the ground, but it's penetrated through the sand. Okay, now so between here and here, we're told that it's 50 cm or 50 meters, and between sand and penetration, you have 5.0 cm. So it still went, buried into the sand, 5 cm. Okay, so calculate the velocity with which the body hits the ground. So this velocity at this point, when it hits the ground at this point, what's the velocity there? U here is 0, V here is maximum, is something. You need to find it. Like I said, let us also recall all our linear motion formulas. The first one we're going to be using here is V square is equals to U square minus 2GS. Okay? Why am I using minus? It's plus because of gravity. It's going down. It's plus. Okay, so we are looking for V, right? We have U, we have 2, we have gravity, we have distance. So we can get V. So V square is equals to U. U is U is 0. Why? Because it's starting from, at this point, it has rest. When you leave it, like you are holding the ball at this point. When you leave it, it starts going down. Okay, so that's why U is 0. Plus 2 times 10, let's use gravity as 10, times distance, which is 50 in meters. So V square is equals to 2 times 10 is 20, 20 times 50 is 1,000. Yes, I'm correct, 1,000. So V is equals to square root of 1,000, and V is equals to what? 100. Sorry, let's say 100. 31.62 square root of 1,000. 31.62. Meters per seconds. Meters per seconds. Okay. So that is for So I've gotten this one. Second question says we should find the time taking. So we're going to be using another linear equation formula. Remember, V is equals to U plus GT, right? Plus GT or AT, remember? Okay, so what are we looking for? We're looking for time. The time. We have V, we have U. Now, the time taken to reach here. Of course, U is still 0 because starting from U. But V, we're gotten V as 31.62, right? So I can put everything there. 31.62 is equals to 0 plus 10 times T. We're looking for T now, right? So this is 31.62 is equals to 10T, and T is equals to 31.62 over 10. T is equals to 3.162 seconds. So I've gotten that second parameter, that second question. Now the final question is we need to find the average force exerted by the sand in bringing the body to rest. So we are looking at the force between here and here now. And you know that force is equal to F is equal to MA. If we have force, number 3 now, let me just introduce number 3. F is equal to MA, right? We're looking for the force. We have mass already. Mass is constant, it doesn't change. It's always been 2. But now, acceleration is what we're looking for. Acceleration is how this thing went down. Okay, I need to take off some part of this board so that we can appreciate what we are doing quickly. Okay. Okay, so see where we are. We're looking for F equals to MA. I know that I have mass. Mass is what? 2 kg, but A is not given. How do I get A? How do I get A? Now, I'm going to get A from this other linear equation again. V squared is equals to U squared plus 2AS. Now, we're talking about A, not G. We're not looking at G. We're talking about A. Okay, so when this body got here, we have already gotten this final velocity from the previous question. We've gotten the final velocity from the previous question. Initial velocity also is given. Okay, A is what we're looking for, and S is the distance. All right, now let's analyze this. Now it says the initial velocity at this point, that is between here and here. Initial velocity here is actually the final velocity when this body left here and came here. So we're looking at another instance now, please. This V and U instance, we're looking at it now. This V, this U here, for the body, when the body hits the ground, is the velocity, final velocity of this particular instance. That is when the body is coming from the top to this point. When it comes to this point, it hits the ground. At this point, it's taking the velocity, the final velocity of hitting the ground. Okay, now that velocity of hitting the ground, I've gotten it before as 3 points. No, is it 31? Okay, yes, we have gotten U is equal to 31.62. This 31.62 meter per second is actually the final velocity for that first instance. So it's starting from that point again. Okay, and A is unknown. V is 0. Why? Because V is where it will come to rest. It's come to rest at this point again. It will be moving and come to rest at this point. So there's no final velocity. And the S distance is given as 5 cm. We have to convert that 5 cm to meters. So this is what it is. That's what it is. 5 meters. 0.05 meters, right? Okay, so we just plug in the formula. So we're looking for A, right? We're looking for A. So from here, V squared minus U squared equal to 2AS. v square minus u square is equals to a all over, sorry, v square minus u square over 2s is equals to a. So we're looking for a. Final velocity we have as 0. Initial velocity we have as 31.62 all over 2 times s is what? 0. Let me use normal times now. Times 0.05 is equals to a. Okay, so this way we can calculate it and get a as minus, by the time you calculate this, minus 9998 meter per second square. This minus is showing the direction of the acceleration. That is, that acceleration is actually deceleration. It's bringing the body down. You see, this as it's going like this is slowing down. It's not actually acceleration that is increasing its speed. It's acceleration that is reducing the speed to become 0. That acceleration is called deceleration or deceleration or retardation. This minus sign is showing that this A is deceleration or retardation. Why? Why? Because the body is slowing down. The body is slowing down. I got a minus here. You ask me why did I get minus? Because it's, though it does not affect anything, I will still remove it. But this minus is telling you that this acceleration is the one that is stopping the body. And that kind of acceleration is called retardation or deceleration. If you plot the graph in linear motion, you understand? This one going up is acceleration. This one is constant velocity. And this one is deceleration. This is velocity time graph now. Remember, you have to apply everything. No? This one is acceleration going up. This one is going down, minus a is deceleration. That's what we have here. So I haven't gotten this one now. I can come to this formula. F is equals to ma. I'm looking for F. Mass is what? What's mass? Mass is 2 kg times 9998. Final answer for this is 19996 Newton. Okay, so that is the answer. So we are going to go into another video to discuss the third law of motion. Remember, this particular series is tailored towards those who are preparing for WAEC and JAM, NECO and GCE. So if you like the video, please subscribe to the channel, and note that this particular class is brought to you by Upvision Concepts Academy, and we are actually using New School Physics for Secondary School, written by Ayakowa, PhD. This is the one of the approved materials for people who are doing WAEC and the NECO and JAM exams. So I hope this video has been informative for you. I'd like to thank you for viewing.